All right, today we get to talk about one of my favorite vector operations, and that's the dot product. I love the dot product because it's so simple, and yet it gives us so much information. It's a very powerful idea, and it's based in geometry, it's based in abstract mathematics, and yet it has so many applications in physics and engineering and so forth. So we're going to be talking about the dot product. The learning objectives are here at the top of the section, and you're going to be responsible for all of those objectives. Um, Calculating the dot product of two vectors is relatively straightforward. We'll see that in a moment. Figuring out when they're perpendicular, again, just relies on the dot product. Finding the direction cosines of a given vector, not super important, definitely a low priority objective, but a nice application. Um, and then talking about vector projections, this is really important. This is how we take vectors that are kind of just floating in space and we project them onto directions that we care about. And finally, we'll talk about a physical application called work. The dot product, as I mentioned, is a remarkably simple operation. You just take two vectors in their component forms. The dot product of u and v is just the pair, the coordinate-wise product followed by the sum of those products. So for example, u dot v is u1 v1 plus u2 v2 plus u3 v3. And you might imagine, well, that seems pretty random. Like, why would I ever want to do that? And it turns out that this seemingly random operation actually yields a tremendous amount of useful information, this particular quantity. The thing to note here first, I guess, is a little bit of dimension analysis. U and V are both vectors, and the dot product of U and V is a scalar. See, it's a real number plus a real number plus a real number, so it's a scalar. And that scalar carries with it a lot of information. For example, if this turns out to be positive, then what we know is that u and v kind of point in the same general direction. They both kind of point like this. And if u dot v is negative, then they kind of point in opposite directions, sort of like this. So these two vectors would have a positive dot product. These two vectors would have a negative dot product. And then finally, right in the middle, the sweet spot, is this situation where the two vectors are perpendicular. In that situation, the dot product of the two vectors will be 0. And so dot products provide a really easy test for whether two vectors are orthogonal or perpendicular to each other. Orthogonal and perpendicular are synonyms. It just means that there's a right angle between the two vectors. Calculating dot products, I'm going to leave that to you to work out. Some properties of the dot product. The dot product is commutative, meaning u dot v is the same as v dot u, and that simply follows from the fact that multiplication in each of these slots is commutative. u1 v1 is the same as v1 u1, and so on. The dot product distributes across vector addition, so u dot v plus w is the same as u dot v plus u dot w. It plays nicely with scalar multiplication, and this fourth property is also an important one to remember. It can save you some time in a pinch and certainly is useful in theoretical calculations, and that is that v dot v is the length of v squared. Well, if you remember, the length of v is just the sum of the squares of the coordinates of v square root. Well, if you think about what v dot v is doing, it's the sum of the square of the coordinates of v. All you're missing is the square root, and that's why this is the magnitude squared instead of just the magnitude. But super useful thing to remember. All of these are very useful properties to remember. There are proofs here. I'll leave those to you to read. Here's some exercises again. I'm de-emphasizing the computational part of this. I'll leave that to you to work out. Now, one of the really powerful parts of the dot product is this relationship between the two vectors, the dot product, and the angle between them. This is sort of the heart of the geometric utility of the dot product. It turns out that the dot product of two vectors is equal to the magnitude of u times the magnitude of v times the cosine of the angle between them. And this really important identity, one that you should memorize, follows directly from the law of cosines. You may not remember the law of cosines, but this is essentially a relationship between the three side lengths of a triangle and one of the angles. And we can write a triangle in terms of vectors strategically, and one vector is u, one vector is v, the angle between them, use the law of cosines, and out pops this identity. If u dot v, if u and v are perpendicular, then we know that the angle between the two of them is pi over 2. The cosine of pi over 2 is 0, and so we can conclude that u dot v is 0. And it goes both ways. If u dot v is 0, then we can conclude that the cosine of the angle between them is pi over 2, aka they're perpendicular. Okay, couple of applications here. We can find the angle between a pair of vectors by computing the dot product. In other words, the left-hand side here, computing the magnitude of one, the magnitude of the other, and dividing. You can see that here in this quick example. So if we want to find the angle between these two vectors, we just simply solve for the cosine of theta. That's the dot product of the two vectors divided by the lengths of the two vectors. You compute the dot product in the numerator, the lengths of the two vectors in the denominator, and you end up with minus 2 over root 42. That is the cosine of the angle between the two of them. And furthermore, if you want the angle itself, you can just take the arc cosine. One thing that we do learn from this calculation is that the angle between these two vectors is obtuse, meaning larger than 90 degrees, as opposed to acute, meaning less than 90 degrees. Because it's negative, these two vectors are kind of pointing in opposite directions, more or less, and so the angle between them is greater than 90 degrees. You see a discussion of that here with some nice diagrams. Again, this is an acute angle between u and v. We would expect the dot product to be positive here. This is an obtuse angle. We would expect the dot product to be negative. Here they're pointing in exactly the opposite direction, so we would expect the dot product to be negative. And here they're pointing in exactly the same direction. We would expect the dot product to be positive. In this last case, they are pointing in orthogonal directions. Here we would expect the dot product to be 0. Indeed, vectors are orthogonal if and only if u dot v is equal to 0. So if they're orthogonal, then the dot product is 0. If the dot product is 0, then they're orthogonal. The implication goes in both directions, and here's a proof. How do we identify orthogonal vectors? The easiest thing to do is just take their dot product. So you're given two vectors p and q here. Take the dot product. 10 plus 0 minus 10 is 0. So these are orthogonal. You can do the dot product in your head. 10 times 1 plus 0 times 3 plus 5 times negative 2. 10 plus 0 plus negative 10 is 0. They're orthogonal. You can find the angles between two vectors by computing the dot product. If you, for example, want to find the angle between this vector 2, 3, 3 and the x-axis, you could, for example, look at the dot product between v and I. In fact, when you're computing the angles between a vector and the three coordinate axes, x, y, and z, they actually have a special name. They're called direction angles or direction cosines, and you can compute these angles by using the dot product cosine identity and the three vectors I for the x direction, j for the y direction, and k for the z direction. Probably one of the most useful aspects of vectors, of the dot product is extracting components that we're interested in. Oftentimes we're given a force, we're working with a force, and we're interested not in the direction that the force is acting, but in some other direction. The dot product provides us with a tool to figure out how much of this force is acting in a particular direction. And it's called the projection of V onto U. So, for example, we're looking at this force. We want to know how much of this force is acting in this direction. It's not all of the force, right? If all of the force were acting in this direction, the force vector would be parallel to this direction. So we can use the dot product to take F and figure out how much of F is acting in this direction, and if we wanted to, what's left acts in the other direction. It's pretty straightforward. You take if you want to find sort of the projection of V onto U, you can use a formula like this. So let's kind of break it down for you a little bit. Remember when we talked about unit vectors, this is a way of sort of separating the direction that a vector has from its magnitude. So if we take the dot product of V onto a unit vector, what we're going to get is the amount of V in that direction. Now, most of the time when we're projecting into a particular direction, the direction that we're interested in is not a unit vector, so we have to take that into account. So what we do is we take U dot V, we take U and we normalize it, U over the magnitude of U, and then we dot it with V. And what this tells me is the length of the part of V in the U direction. And then I take that length and I multiply it by the unit vector in the U direction. And then I do a little bit of simplification and I end up with the vector projection. This is the projection of V onto U. It's U dot V over the magnitude of U squared times the vector U. This is a vector quantity. Here, U dot V is a scalar, the length of U squared is a scalar, and U is a vector. A scalar times a vector is a vector. Sometimes we don't want the whole vector thing, we just want the length of, or the magnitude of V in the direction of U, and if that's the case, all we need is this piece right here, U dot V over the magnitude of U, and that's what this is. So we have two notations here. The projection of V onto U is the vector component of V in the U direction, and the scalar projection, comp U V, is the length of V, or the magnitude of V, in the U direction. Both of them are useful, and we'll use them frequently in the rest of the semester. Here's a nice visual, and this is sort of what I carry around in my head. Here's the vector V. How much of V is pointing in the U direction? Well, it's represented by this orange vector. How do we figure out what that orange vector is? We take U dot V over the magnitude of U squared times U. That is precisely this orange vector. If we want to know the length of this vector, the length of V in the direction U, then it's a little simpler. It's just U dot V over the magnitude of U. And we take the absolute value of U dot V because this could come out to be negative, and the scalar projection for our purposes is going to be positive. So finding projections, you can use these formulas, this one for the vector projection, this one, and this one for the scalar projection. I think it's more important as a takeaway to have this picture in your head. This kind of tells you how much of V is pointing in the U direction. There are a number of exercises here that you can check your work with or check your understanding with. We'll wrap this up with the notion of work. Work is when you have force times distance. It's a physical quantity, and the dot product plays very nicely with work. It turns out that if you have a force acting in the direction, say from P to Q, you can figure out how much work is done by taking F dot, the displacement vector from P to Q. So I have a force here, and I want to know how much work is done, say pulling this wagon 50 feet. All I have to do is compute this quantity. the magnitude of f times the magnitude of PQ times the cosine of the angle between them. The magnitude of f is 8 pounds. The magnitude of PQ is just the length that I moved in that direction, and the cosine of theta is just the angle between the direction of the force and the direction of motion. All right, let's do a few exercises. Okay, let's try problem 132. In 132, and indeed all of these problems, you're asked to find the measure of the angle between the two given vectors and express the answer in radians rounded to 2 decimal places, and then also figure out whether the angle is acute. So let's find the angle between A and B here. These are two-dimensional vectors. These identities all hold for really any dimensional vectors that you could want. So we're going to use the cosine identity for the dot product, which says that A dotted with, let me get my pen on here, A dotted with B equals the magnitude of A times the magnitude of B times the cosine of the angle between them. In 132, which is what we're working on here, A dot B is -2 plus 3. -2 plus 3, that's 1. The magnitude of A is just 2 squared plus 1 squared, square root of 5, times the magnitude of B, which is 1 squared plus 3 squared, square root of 10, and that's the cosine of theta. All right, if we solve for cosine of theta, we get 1 over the square root of 50. If you don't remember the rules for square roots, yes, you can take those square roots and merge them together to get 5 times 10, 50. And then finally, theta is the arc cosine of 1 over square root of 50. This is not an angle that I'm familiar with, so I'm going to jump over to Google and ask Google what it is. So let's take the arc cosine of 1 over the square root of 50, and that works out to 1.43 radians. And that's all we were asked for, to give the answer in radians rounded to 2 decimal places. But just to get some intuition here, and I guess the other thing is to check whether it's acute or not, let's go over to degrees. So let's convert these radians to degrees, and we had 1.43 radians. That works out to be about 82 degrees, 81.9, 82 degrees. That's acute. So this is an acute angle as the answer to part B, because the angle between them is less than 90 degrees. All right, in 142, we want to determine whether the given vectors are orthogonal. Now remember, the dot product provides a really easy test of orthogonality. If the dot product is 0, then the vectors are orthogonal. So if we want to figure out orthogonality, I'll just repeat the question up here briefly. Are they orthogonal? Let's look at A dotted with B, A being x comma x, and B being -y comma y. The dot product is -xy plus xy, which simplifies to 0. So in fact, A and B are orthogonal. Dot product, you gotta love it. Let's look at 46, 146 that is. So in 146, find all two-dimensional vectors that are orthogonal to 5, -6. So this is a sort of a little bit more advanced question. It sort of requires you to build a solution in several steps. So let's talk through this. All right. Well, look, if you're going to be a vector A and you're going to be orthogonal to B, what has to be true? Well, A dot B has to be 0. That's an if and only if. So we want A dotted with B to be 0. Now, A is currently unknown. A is unknown. If we want to figure out what A is, we have to figure out each of its coordinates. So let's give them unknowns. Each coordinate gets a variable, an unknown variable. All right, well, A dot B has to be 0, so that means x, y dotted with 5, -6 has to equal 0. That means that 5x minus 6y has to equal 0. If we solve for y, we get that 5/6 x equals y. What did I do there? I just moved 6y over to the right-hand side, divided by 6, and I get y is equal to 5x over 6, or 5/6 x. It says find all two-dimensional vectors A that are orthogonal to B. All right, well, if x is just x, we know that y is equal to 5/6 x, and this is the generic form of such a vector. And since x is a real number, we could actually factor it out, and what would be left behind is a constant vector, 1 and 5/6. And what we learned from this is that there's a whole family of vectors that are orthogonal to B. And we can visualize this if we carefully plot. Let's plot B, 1, 2, 3, 4. Oops, looks like I put my coordinate system in the wrong place here. Let's raise it up a little bit. X and Y. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6. There is B. And let's get a look at this vector. There's the vector B. Let's get a look at this vector, this part of A that's constant. It's 1 and 5/6. So over 1 and up 5/6. It's about right there. Let's put that little vector in there. Now, that's not the only vector. X can be any real number. So what this actually represents, again, this is scalar multiplication of a vector. What does scalar multiplication do? It stretches and shrinks vectors. So if I make X really large in the positive direction, I'm going to be stretching this vector out in this direction. And if I make it really large in the negative direction, I flip its direction and make it large in the other direction. And all of these vectors along here, all of these vectors, you'll notice, make a right angle with the given vector B. So how many vectors are there that are orthogonal to 5, -6? There's a whole family of vectors, and they are all the vectors that are parallel to 1, 5/6. So you learn quite a lot just by thinking about these geometric properties of the dot product. Let's look at 162. In 162, we want to find the direction cosines for the vector and the direction angles in degrees. All right, the direction cosines are just the cosines of those dot products associated with those dot products, and then the angles are the actual arc cosines. Let's look at 162. And remember that the way that what these are the angles in the um, in in the x, y, and z coordinate directions. So alpha is for the x-axis, and we'll use the standard unit normal vector I. Beta was the y-axis, and that's going to correspond to j, and gamma is the z-axis, and that's going to correspond to k. All right, so we're going to work on 162 here. Let's write that in component form, 1, -2, 2. All right, and if we want to find angle information, we have to use the angle formula, the angle identity. So u dotted with I is the magnitude of u, magnitude of I, times the cosine of the angle between them. U dotted with I, remember that I is just 1, 0, 0 in component form. U dotted with I then is just 1 times 1 plus 0 times -2 plus 0 times 2, and that just works out to be 1. So on the left-hand side we have a 1. What's the magnitude of u? Well, it's 1 squared plus 2 squared plus 2 squared, which is 9 square root 3. What's the magnitude of I? It's just 1 squared plus 0 squared plus 0 squared square root, so that's 1 cosine theta. So we know that the cosine, the direction cosine for the x-axis, the direction cosine, alpha, and I should have been using alpha here all along, is 1/3. And of course alpha is the arc cosine of 1/3. And then you can jump over to Google and check that out. Similarly, you can do j and k. In all three cases, I, j, and k, this part of the identity will be 1 because I, j, and k are unit vectors. Their lengths are 1. But the other angles will change. Okay, let's look at problem 172. You're given a couple of vectors in terms of the standard unit normal vectors, I, j, and k. We're going to find the component form of the vector w, that is the projection of v onto u. And then we're also going to write v as a decomposition of two vectors, w, which we computed in the first part, and q, which is turns out will be orthogonal to w. So let's work out part A first. In part A, we have, well, actually, before we do part A, let's write u in terms of its coordinates. So that's 2, 4, 0, and v in terms of its coordinates, 0, 4, 2. And let's remind ourselves that the projection vector in the u direction of v is given by u dotted with v over the magnitude of u quantity squared times the vector u. U dotted with v is just, let's see here, 2 times 0 plus 4 times 4 plus 2 times 0. That's going to be 16. And the length of u squared is 4 plus 16, that's 20. And then the vector u is 2, 4, 0. Let's simplify this as much as possible. This simplifies to 8/5 and distribute it in onto the components. So we get 16/5 in the first coordinate. We get, we get 8/5 in the first coordinate. We get 16/5 in the second coordinate and 0 in the third coordinate. And this is the vector w. All right, to answer part B, we first need to compute q. So we're defining q to be v, to be part of this equation. And so we know that q is equal to the vector v minus the vector w. What's the vector v? It's 0, 4, 2. And the vector w we just computed is 8/5, 16/5, 0. Let's do a bit of arithmetic here first. We subtract coordinate-wise. So the new vector q is going to be minus 8/5. 4 minus 16/5. 4 is the same as what? 20/5. 20/5 minus 16/5 is 4/5. And then finally we have 2 minus 0, which is 2. Okay, this is the vector q. And what's interesting about this, just from a geometric perspective, if you take the vector v and you remove the part of v in the u direction, which we computed earlier, that's w, then this should be, what's left should be orthogonal to u. So you removed all of the u component from v. What's left should be orthogonal to u. And we can verify that. This isn't part of the exercise, but we can verify that by simply looking at q dotted with w. Minus 8/5, 4/5, and 2 dotted with w, 8/5, 16/5, and 0. Dotting these, you get negative 64/5 plus 64/5 plus 0. You get 0, and so we can conclude that q is actually orthogonal to w. This will always happen. So if you remove the component of v in the u direction, what's left behind, q here, is going to be orthogonal to u. Really interesting and powerful idea. All right, let's talk about exercise 173. So 173 is a bit of a chemistry application, and this is a totally legit thing that people want to do, especially in sort of crystallography. These kinds of geometric questions are really important, and the dot product plays an important role. We have a methane molecule that is sort of tetrahedral in nature. And let me make a little bit less space here. And a little bit more space down below. All right, we want to find a distance between the hydrogen atoms located at P here and R. And how do we do that? Well, we could just use the distance formula on these 2 points, or we could take the displacement vector from P to R and compute its magnitude. They're equivalent processes. So in A, let me change back to black here. In A, we're just going to look at the magnitude. Yeah, let's look at the vector from P to R. Okay, so we have P, R is the vector -1, -1, 1, -1, and 1, -1. And the magnitude is going to be the distance between these 2 points. So the magnitude of PR is the square root of the sum of the squares. And that is the square root of 8, which simplifies to 2 root 2. So the distance between these two molecules, or sorry, between these two atoms, is 2 root 2. Now find the angle between OS and OR. So that's the second part of this question. OS, kind of pointing out of the screen, or maybe back, I don't know, but back to this vertex here. Here's S, and OR out to this. And of course, we know that if we put the origin here, or we have put the origin here, and we write this in component form, then I'm just going to use S as a vector. It looks like this, and R as a vector. It looks like this. And we want to find the angle between OS and OR, between these two vectors. I guess we could put O in there. All right. Okay, had a little bit of an interruption there at my door. So we want to compute the angle between these two vectors. We're just going to go back to the cosine formula. So we've got OS, that vector, dotted with OR, is going to equal the length of OS times the length of OR times the cosine of the angle between them, theta. Well, we can do that. Make a little bit more space here. Let's do OS dot OR, so that's -1 times -1, 1, plus -1 plus -1. That's going to work out to be -1. All right, so just double checking here. Yeah, that seems good. Okay, what's the length of OS? It's just the square root of 3. And the length of OR is also the square root of 3, and then cosine theta. So the cosine of theta is -1/3. And then we can go to Google or grab your calculator or something and figure out what the arc cosine of -1/3 is. Let's do that really quickly. So that's 1.91 radians. And as degrees, let's see what that looks like as degrees. We would expect this to be a little bit bigger than 90 degrees. 109 degrees, so there are 109 degrees between these two vectors in this particular molecule. Like I said, crystallographers use this. It's really important in scattering theory, that kind of stuff. All right, last, not least, 178. So in 178, we've got a car that's being towed under a force of 1,600 newtons. And we want to find the work done if we tow the car 2 miles. Let's draw a picture here. So we've got the car. You can sort of make fun of my artistic skills here, and here's the tow rope, and we've got 1,600 newtons in this direction, and it makes an angle of 25 degrees here, and the work done is going to be the magnitude of the force times the magnitude of the displacement, which we'll just say the length of the trip. Times the cosine of the angle between them, 25 degrees. And we can just fill in all the bits. The magnitude of the force is 1,600 newtons. The length of the trip is 2 kilometers. If we want to do this in meters, we're working in meters here, that's 2,000 meters. And then the cosine of 25 degrees, let's go the other direction here. So let's do 25 degrees. That's 0.44 radians, and we want the cosine of 0.44. That's going to be 0.9. And we can then just kind of do the full calculation. 16 that works out to be 2.9, let's say, yeah, 2.9 million joules. Okay, the suggested exercises for this section are all of the exercises, but I'll remind you that you don't do them all, you just kind of do enough in each section to get an idea of how problems work. Once you're comfortable with the concepts here, then jump over to WebWork and do the assessment for Chapter 2, Section 3. Thanks.